Uh, yeah. Good afternoon, all. Welcome to Machine Learning for Material Sciences. I think we have been through now this will be the 18th lecture. I hope you have gathered more or less like what machine learning is all about. From machine learning point of view, we covered supervised learning, we covered unsupervised, we covered linear regression, yes, and we covered a little bit on what attempts can you make to solve basically um, some of the feature engineering problems. What if a data point is missing? What if the feature scales are not matching? And what are the like performance metrics that you should care about while doing regression or classification? Yeah. And last time we talked a bit about the bias and variance. So we will continue that discussion because that discussion, whatever we are going to talk today, we will require that discussion as well as we'll introduce to you ensemble learning. Yeah. Uh, Fine. Yes. We will cover via bias and variance again. The trade-off specifically, like you cannot have how do I say, you cannot have something that is very good in bias or very good in variance. So this is just a question because you have attended, okay, 1 week back the class. So what do we expect a model to be in bias or variance? Like, should it be low bias, low variance, or high bias, low variance, low bias, high variance? If you can type it somewhere or chat it. Yeah. I would just like to hear if we are on the same page. Anybody remembers about bias and variance? Okay. Uh, Fine. Then, okay, so what we expect a model, then we go back to the definitions of bias and variance, right? So we understand it from that point. Uh, Bias is what? If it has to make, basically bias includes it that the model makes very less errors, like during training, right? And like variance would be uh, if we change the input very slightly, the model parameters should not change a lot. So, and bias also comes from the idea that you make a lot of assumptions about data. Generally, how do I say, the models that are less complex, they end up having high bias. Yes. And models are very complex, they end up having low bias. Yes. But what we expect out of this is low bias and low variance model. Yeah. And so how regularization affects this trade-off? We have covered this in the last class. I'll just repeat some of the parts today again, and then we'll jump to ensemble methods. Yeah. And under ensemble methods, generally there are two categories. One is the bagging, the other one is boosting. Both of them we will cover. There are many variations of this bagging and boosting, but we will cover only random forest and gradient boosting today. Fine. We are here. So like the bias and variance. So bias like error for oversimplifying assumptions. What we do is like if something has very high bias, it will start underfitting. Yes, the true relationship. Here it means basically if the true relationship was, let's say, nonlinear and you had linear regression which had like high bias, then high bias could lead to errors. Yes. And variance is basically if there is small changes in the input data set, then the like relatively large errors occur. Yes, the model parameters need to be changed by a lot, let's say. Yeah. And basically, if you do away or if you end up with doing high variance, you end up with something called an overfitting. And overfitting is basically you end up with very high errors in the test set. Yeah. uh, so these are the bias and variance definitions. And what do we have? So for example, high bias models, they're basically one of the example is linear regression on non-linear data, and shallow decision trees. So I hope you remember decision trees. If we go really down, that means we are remembering. If we don't, if we go up, that means we are saying one question is enough or two questions are enough. Yes, there are a lot of assumptions takes place that if we just ask questions on two features, we will get our answers. That is still a very high bias model. Yes. Low bias meaning we ask the entirety of the decision tree to get. Yes. So any assumption that we make about the data, basically that evolves into high biasness. Yes. And what do we end up if we have like a high bias method? So basically we end up with poor performance on training set. Of course, if we do poor in training, it's not a, of course like, but we might end up with poor performance in test set, but high bias models do end up. And we do consistent predictions but wrong predictions. Consistent in terms of linear regression would give you output on some level that you can understand, and specifically high bias model end up in something called underfitting. Yes. The example was, I think, clear. I've been repeating. So it's a linear model for a quadratic relationship. Yes. Okay. So the next is a high variance model. So this is the particular case where like a small change in the data itself can produce larger variations in the model's parameters, let's say. Uh, One of the examples are like deep neural networks. They're like very large, but if you change the data, uh, little data if it is used, sorry, if like very large networks and data set is very small, and if those small data set change a little bit, your entire neural network will change. We'll cover our neural networks later. But assume this has a lot of parameters. Yes. So anything that has, let's say, a lot of W and B's, but you have very little data to start with. So if those small data change minorly, all these W's and B's will change. Yeah. So, and also deep decision trees. So the like the disadvantage of like choosing the smaller shallow trees is underfitting or high bias. Or if you go to the depth of the tree, then you end up with basically high variance. Yes, because then your answer exactly depends on an example, and if an example changes, your answer also changes. Yes. So these are very complex models with very high parameters, generally high variance. Now, what are the characteristics? Basically, generally high super complex models, they will perform really good on training set, but they will perform really bad on the testing set. Yes. And this is particularly known as the overfitting problem. Anytime you see really good performance on training set but bad on test, that means you're overfitting. Yes. And overfitting meaning you have high variance models, so you need to do something around that. We will cover here also what to do when this happens. And then predictions change dramatically with new training areas. I told you, like if you change data set little bit, it will do. But the same neural networks with a larger amount of data can do really well also. Yeah. So now the bias variance decomposition, this comes from largely a theoretical background, but that's not important for this particular course. So I just want to tell you the total area will be like total error will be equal to bias square variance, and you know, that sigma square will come back. Bias will be most likely because the model itself has issues, right? Doesn't matter what you do, variance and like let's say sigma square, whatever those, if you even if you remove those, bias will remain if you chose a wrong model. Yes. Variance is basically the training data variations. That means either you chose very less data and super complex model, then this variance will come into picture. Yes. And sigma square is irreducible noise. Basically, data inherently is just noisy, right? So basically, maybe you want to find something in the image, but the image itself has a low resolution. So that can be also kind of noise because you don't have very high resolution to exactly point out. Yeah. But here the only like the takeaway from this particular entire exercise of bias and variances, generally and most usually, so we cannot reduce both bias and variance. And ideal would be to find out a model which is both low bias and low variance. Yes. So now what do we do? Yes. So if we choose simple models such as linear regression, let's say, or distant tree with shallow height, they will have high bias but low variance. Yes, they will be very consistent in the output, but they will be most likely wrong. Yes, examples are linear regression, logistic regression, all those like easier models that we have studied. Now, complex models again, if we choose, they are super highly complex, as in they have a lot of parameters to train. They will have low bias, that means they will not make any assumptions about the data, and they will have less errors during training. But they will end up with having like high variance, because if model changes a tiny bit, everything changes. Yes, these are accurate, of course, but they will have very inconsistent predictions. And examples are deep neural networks or very deep decision trees. Yes. So then what do we do? So we have to find a balance. One of the ways we found balance is by regularization. We looked at it last time. Both lasso and ridge regression as you, or L1 and L2 regularization, you basically add a C term, and you basically have the loss itself. That could be MSC loss, or like cross entropy, or let's say maximum minimum log likelihood. So all those losses, plus we add another factor called like let's say C is a constant, and then norm of W, the norm of all the weights. Yes, that is the basically the regularization parameter that controls how much regularization you want. That basically tells which of the W should I reduce. Yes, uh, and if I reduce my W, that means that one particular feature goes away, and the model, instead of having 1,000 W's to deal with, it will have only 100 W's. So model inherently becomes less complex. Yes, so it basically forces simpler models, because it, and then because it models becomes simple, and it will increase the bias a bit. Yes, I hope this one is clear. Like, it forces simpler models, but simpler models have higher bias. Linear regression, higher bias. Yes, and then reduces sensitivity to training data set. The moment we give up assumptions, like how do I say, the moment we start removing W's from the model, that means those particular features are basically gone. So that means even if those features change, no impact on the entire model. So that's why it reduces sensitivity to the training data set, and generally they offer better uh, results in test. Yes, so small c, large c, we discussed this one. Uh, the more point is more regularization, higher bias and low variance, and large c, if we take it, to end up with lower regularization but lower bias and high variance. So takeaway again is like either we can lower the variance or lower the bias, but not of them, not both of them add together. Yeah. Now, of course, like how do you choose? Of course, like if we don't do regularization at all, we end up with high variance, low bias. Some kind of regularization, if we use, we will expect lower variance. That will help us. A little bit bias will increase, but that is okay. But don't do also over regularization. That means you don't make C super high so that everything goes to zero. All W's go to zero. There is only one W left. Then that W is dependent on only one feature, which might be important, might not be important, but that does not give us enough information. So that leads to underfitting. Yeah. Okay. So this was all the previous classes, right? And regularization, you remember? So regularization moves a complex model to less complex. So complex models basically they generally have, let's say, high variance. So if you can imagine in your head like the four boxes, let's say low bias and low variance we have on the top, let's say one of the areas. On the right hand side we have high bias and low variance, high variance and low bias. So from high variance to low bias, we are moving up to low bias and low variance area by using regularization. Yes. Now, the other way to tackle this, okay, so regularization is not only done by L1 and L2, rather there are many other methods to do L1 and L2. We talked about something last time, dropout is there, early stopping is there. Those are some manual methods that we do. Dropout though is like a proper regulation, but there are some manual methods like early stopping and all that stuff. They also help in doing regularization, some level of that. Uh, and we will discuss as we jump to neural networks. The other way to think about this is called ensemble learning. Yes, this is majorly done to treat this bias and variance trade-off only. Uh, so here, as it says, like the core principle is instead of learning one super accurate model, like having a very deep neural network or a very large tree that is absolutely correct. Rather, what you can do is you can train many such low accuracy like models, and combine their predictions. Yes. So instead of training some one person to be too good, he will end up with maybe overfitting. Rather, I will train like few low quality models, and I will take an average of those guesses, like whatever those models will give me. I'll either make an average or some kind of combining strategy I will use, and then eventually I will find the answer, right? So key insight again is the wisdom of crowds. Basically, multiple weak learners can create a strong meta model. Yes. So instead of training one model, I will train many models, but those are relatively weak. They are not super accurate, but they're relatively weak. But together, they will make a very big, nice model. Yes. And each weak model, of course, must be better than random guessing. Like it should not be super weak. So it should be better than random guessing. I hope this random guessing is okay, right? So if I have three classes to predict, if I guess randomly, then I will have like a 0.3 probability of getting it correct, right? 0.33 or whatever. Yes. Ignoring those very typical probability stuff will come back, but let's say 0.33 is the probability I will get it correct. That is random guessing, right? So my model, when I develop, it has to be better than 0.33. It should not make more errors than a random guessing. Yes, the weak learners at least have to have this. Now, the models should make different types of errors. So here what happens is, if I train many low models, let's say low quality models or low accuracy models, they should not be exactly the same. If they're exactly the same, then what happens? Then basically, even if I take an average or a combination, doesn't help, right? So I have to train different models, but they have to be absolutely different because they have to give me different type of predictions. And to give different type of predictions, here it is written that they have to make different types of errors. Yes, we will cover that. So, and then we have to have some strategy how to combine all those weak learners into one of them. Hmm. Now, like why ensemble works, this is important question to ask basically. Yeah, individual weak models, if I train a weak model, let's say, which is easier to predict and easier to learn, let's say, it is first of all very fast to train. Yes, if it is weak also, it does not have, let's say, many parameters or so. It does not overfit. And because it does not have many parameters, it is also faster to ask for inference or prediction. Yes. So if I have to do 1,000 W's, if there are 1,000 weights and there is another X of 1,000, multiplying 1,000 W with 1,000 X vector will take more time, let's say, than 100 W and 100 X. Yes. Uh, or even compute time or time, it will take less. Yes. Now, how are they generally? They're generally shallow decision trees. That means they're decision trees, but the height will be less. Yeah. And what we understand is, at least the height has to be at least this much so that they are better than the random guessing. And they also shallow different trees, as previously told, they should not make the same mistakes, rather, and which ends up as which they should not make the same inference or the output. Now, combined strong model, because we do a weighted, let's say voting, we can do weighted voting as well. There are many other methods to do a voting. And the major thing comes from here, that the good models will agree on correct predictions, bad models will disagree on incorrect predictions. I hope you understand this particular point, because this is the entirety why Ensemble do. Generally, if I train a few models, if they're right, if they're pointing to the right one, matlab if they are correct, most of the good models will point to the same answer. If they are wrong models, that means they are not right models, some of them will not be trained to the perfection. But because we have trained them to predict or make different errors, they will predict the wrong ones, but all the wrong ones will be different. I hope that makes sense. Yes. All the good ones will point to one correct prediction. All the wrong models will point out to multiple incorrect predictions. Yes. So this is what we leverage here. And if you do a majority voting, we understand this, all this 10 good models predicted one, all these 5 bad models, they predicted, let's say, 2, 3, 4, and 5. So because there is no combination between these 4 or 5 wrong models, by majority, one will win, which is the correct answer. Yes. And we win because they are faster to train, faster to predict. Yes. I hope the concept is clear. This is entirely what ensemble does. Yes. And just generally, again, shallow decision trees. So how do we create shallow decision trees? I think I have told when we discussed decision trees, but some of the things. So after few questions of feature asking, I hope you remember decision tree. So we create a root node, the first node, which is basically what feature I'm asking question to. Yes. And then based on that, the entire data set in the rows splits. That means if a data set had columns, let's say uh, temperature greater than 38 and less than 38, if the first box of the feature is like temperature greater than 38, the data set splits into greater than will come to the left hand side and the less than will come to the right hand side. Then we will ask another feature the question on the split data set, and so on and so forth. So what we do is basically we stop splitting. That means we have only few levels of decision tree. And because we're asking only few levels, it definitely won't be accurate. But because we are only doing few levels, it will be super fast to train and super fast to predict also. Yeah. And each tree should see different aspects of data. Yes. This is what I will tell you how they do it in some time. Why trees? First of all, they can handle nonlinear relationship. I hope you remember that figure that we had. So that was a figure, there was a each individual feature does a straight cut. But if we take multiple nodes, multiple levels together, they will have this cut, that cut, this cut. Yes. So together they will have a nonlinear cut. But each feature will have a linear cut. Yeah. And these are naturally they handle mixed data types, and they're easy to make diverse. That means you can choose whatever the splits we have, choose where you want to stop, how many labels they can have. Now coming to the what actually happens in practice, there are two ensemble I told you. One is like bagging, the other one is boosting. uh, so bagging is basically one of the popular algorithms in bagging is random forest, if somebody knows. Yes. Here, what happens is you create. Sorry, so before that, it reduces the variance of this, right? I'll come back to how. But first is basically you create multiple copies of training data. So you have, let's say, 100 rows. What you do is you create again another 100 rows. Yes. And here, what you do is you train weak learners on different samples. So if you create multiple bags, so here bagging is basically you create multiple bags of data set. But here, when you create a bag, okay, let me just revisit. Maybe I'm losing a few. So you have, let's say, 100 rows of data. Fine. Now what I will do is I will create multiple copies of this data. Yes. Each copy is called a bag, let's say. Yes, that's why it's called bagging. So now earlier I had just 100 rows. Now I have created, let's say, 10 bags of each of 100 rows. Now, how do I create each bag? I will sample like basically with and I will sample data sets like rows from the original data set into this bag. Yes. And I will do it with replacement. Yes. So that means I pick one, I will put it back also. That means I can repick the same dead row into the bag. That means if the original had 100, the new one can have unique, let's say 90. The 10 might be repeated. Yes. So here, if I continue to do this sampling, every bag will have different data set altogether. Yes, because I'm sampling with replacement. Yes. So now if I do that, each of my bag has overall the same data set, but there is still some variations in each data set, each of the bags. Now, if I created 10 such bags, I will train my weak model, that is a shallow decision tree, on each of the bags. Yes. Now, once I train each of the shallow trees on each of the bags, I will whatever now they predict, if a new data point comes, I will ask each of the 10 models to predict what they think, basically whatever they want to predict. And once they predict, I will combine them. Yes, this is the overall idea of bagging. One of the examples that is there is random forest. Random forest does one more additional thing. So just to point, let me see if I've added it here. Okay, yeah. I will come to the random for that one additional thing, but bagging again, you pick a data set, you make multiple copies of the data set, but just not direct copy, rather you like sample data sets from there. You create exactly 100 rows, but because with replacement, so you can, same row can come multiple times in one bag. Yes, and then you create low models across all of the bags when you do a combined strategy while prediction. That is your bagging. Next comes boosting. Boosting is basically the same. We start with weak learners only. There is no problem. But what we do is, let's say we have to predict y, given x, we have to predict y. So now we trained a weak model, right? So a very shallow decision tree, let's say M1. Now M1 will, given x, M1 will predict, let's say y1. Yes, but y and y1, there will be some difference. That y minus y1 is the residue, right? So what we will do is we will again train another model M2 that will take x as input, but that will try to predict the residual from the previous model. That means y minus y1. Yes. Initially, we tried to predict x to y. We trained a model M that took x and predicted y, but he predicted y1. Now we train another model M2 that takes x again but predicts y minus y1. Yes. Then we predict again another M3 which tries to predict, like let's say newer y minus y1 minus y2. Yes. Every time we train one more model that tries to correct whatever the previous model has missed, because y minus y1 is the error that we got in the M1 model. M2 will try to fix that particular error. Okay, let me try to predict that particular missing value. So similarly, M1, M2, M3, M4, I will have a series of weak learners. Every learner will try to correct the previous model. That means the first model will give us some error. Second model will try to reduce that error. Third model will try to reduce more. Slowly, slowly, slowly. Yes. And then that is what it's saying. Each learner fixes the errors of the previous model and it is combined again with a weighted voting. We'll come back to that. One of the methods that people use is called gradient boosting. Yes. Now we'll just move on to, let's say, bagging. Bagging, I told you, like if you create B random samples from SP, let's say from the training set, you sample with replacement. This is bootstrap sampling, otherwise known as bootstrap sampling. Then each sample, as in the each bag, must have the same number of data points. If the original data set has 100 rows, the each bag should also have 100 rows. Yes. And each sample will be different because we are sampling with replacement. Yes. Now we train a decision tree FP on each sample SB. Yes. And then we combine predictions. If it was a regression, we ask for just a mean, maybe. If it was a classification, we ask for majority of voting across all the models that we created. Yeah. Random forest, as I told you, it does a little bit more than general bagging. So here the problem with vanilla bagging, now trees become correlated. So the idea is basically, even if you do this sampling, no, the most of the data points still match and the trees eventually become correlated. That means what will happen is, because there's shallow decision trees, right? We are asking a few features, and most of the times, generally, the few features that are there at the top, they really do not change. So what happens is, eventually all the shallow decision trees will look exactly the same because the top few features we ask questions on are the same. Yes. So basically that's what it's saying. Strong predictive features dominate the splits. That means the shallow decision trees, there will be few nodes in the labels. Those labels remain constant across all the things. So now many trees will use the same features. Now this correlation will reduce the ensemble benefit. The one idea that we had that each of the trees will have different errors, that won't happen because most of them have the same features or the same nodes in their decision tree. So what do we do in random forest additionally? So here we do also something called a feature randomness. So all I have talked about bagging is how you split the rows. Yes, like you make the data points into bags. Yes, here what we do to mask, or basically we remove of features as in columns, right? So every time we get, let's say, 100 rows we do into bags and everything else, that is done. But while we train the silo decision tree, we randomly remove some features when we move from label to label. That means, let's say, in the starting point, let's say it had 10 columns, let's say 10 features. We randomly choose a subset to be in the, let's say we choose only 7 features. We remove 3 of the features from the decision making. Yes. So in a way, what we're creating is basically we are hoping that at least it will create some variation in the decision tree. Because if you remember, the nodes itself are basically the features itself. We are asking the question, is the weather cloudy, rainy, or sunny? Based on that, we split temperature greater than 38. These are basically the columns. Yes. So here what we do is, instead of taking all the columns, when we are doing a particular split or a training point, selecting one node, we basically choose a random subset of features. Yes. So the earlier problem that we had here, that the many trees will use the same features, that is gone, because now we are trying to consider random subset of features. So this definitely does not super guarantee, but like with probability we can say there is some certainty that all the trees will not look like the same. Yes. So this will basically reduce the correlation between trees, and it forces trees to be different in producing errors, different in predictions. Yes. This is what random forest adds in addition to the bagging algorithm. Yes. Now, why random forest will work? A random forest will work because like multiple bootstrap samples will reduce this overfitting. Yes, bootstrap samples is the bags that we have. So it does. So every model sees different data sets. That is because of the bagging. Yes. And noise and outliers will have less impact, because if you look at the sampling, no, generally noise will be like 1 point. That does not get sampled. So it also, noise and outliers will reduce, and the models will become more stable. And feature diversity, because we are doing random feature selection, it prevents feature dominance. Like the top few nodes will not be the same because we are choosing random features. And it ensures, of course, tree diversity, and different trees capture different patterns. Yes. And here we specifically go back to the same question, like the uncorrelated predictors are definitely essential for assemble success. They have to be different, right? Otherwise, it was the same tree and we do average, doesn't make sense. So what are the parameters, like hyperparameters in random forest? So the number of trees. So that means how many number of bags you choose, because you have original data set, you created multiple copies of this bag. How many copies of this data set? Because each copy is corresponding to one model. So that will also decide number of models. So number of trees is basically that, how many bags you create. So typical range is 100 to 1000 trees. So that means you make 100 to 1000 copies of the data set, and for each copy you create a model. Yeah. More trees is better performance, but after some time you see diminishing returns. That means even adding like another 100 trees won't give you much better performance. Yes. Feature subset size, generally in regression we choose like p by 3, like you reduce it to like p by 3 classification root p features, let's say, and you can fine tune based on validation performance. These are just general recommendation, might work for you, might not work for you. And like tree depth, we can keep it as deep as possible, that is not an issue. But generally like if super depth, it will overfit, so that's the thing. So somewhere in the middle. Yes. Fine. So these are random forest, and the line here says is very nice. Random forest is very popular. Random forest is super popular actually. It handles outliers well, noise pretty well. It is super fast. We have done enough work in decision trees as well as random forest. They're really, really fast. They generally don't overfit because we have more trees which are generally individually they don't overfit. So feature importance also, like we do feature ranking automatically, yes, and because this is decision tree, it can handle mixed data types, categorical and numerical feature because the question is on the feature itself, yes, and missing values, it can also handle missing values, yes. The only problem here is it is not interpretable anymore. In decision tree, we could tell ki, okay, like this is the path we followed to give you the answer. But here in random forest, because there are so many trees, which tree and which path gave you the answer is difficult to tell. Yes. But otherwise, random forest is a very popular algorithm. Not just popular because the hype, it is a really good algorithm. It gives a very good accuracy, it does not overfit, a lot of benefits. The next is gradient boosting. This comes on the boosting idea. So I told you, like each newer model that we create tries to correct the previous model's error. Uh, so each model fixes the errors of the previous models. Key difference in bagging, the models are trained independently because once we create new bags or new copies of the original dataset, we can parallelly train individual models. Yes. But here in the boosting, first I have to find what was the error in the previous model. Right. So in the bagging, all the individual models can be trained parallelly. But in the boosting, I have to first train one model, find what is the error that it gives, then I have to train the second model, then the third model, then the fourth model. What do you think will be faster? Will bagging be faster or boosting be faster? Any anything on chat?
We should have some response to these questions, I think.
Yeah. This is a simple question, right? So, like bagging, what I can do is I'm just splitting the model into multiple bags. Each model is trained individually, and I can do it in parallelly. But in boosting, I have to create one model, find the error, then the next model has to predict the previous error, then the third model previous, and so on and so forth. Like, what would be fast? Fine. Well, response would have been quicker, but fine. So of course, like bagging will be faster, right? Because I can train it very parallelly, right? So, but boosting will be slow because I have to wait for the previous model to get trained completely. Yes. So this is the first point of difference. And like because if you don't have time, then bagging is the way to go. Super fast output. But boosting will generally perform a little bit better, but it's slow to train. So this is how the boosting works. So as in you start with a very simple model, let's say, like let's say the f of x is there, and you try to predict something. Yes, f of x is there. Then the next point is you compute the residuals. Residual is what is the error that you made. Fine. Let's say that is yi cap. This particular thing. Just above I'm selecting, sorry, I'm not able to select the equation, but just above. So basically yi cap is what I'm have, then yi minus f of xi. Yes. So yi minus f of xi will give you the error that I'm doing, that is also called residual. Yes. So now I will train another model called f1 which will try to predict this residual. So my new x and y will be x and yi cap. Yes. So now my updated model becomes f is equal to f0 plus alpha of f1. Alpha is another hyperparameter that I will choose. Like how much of this residual correction I want. Yes, that is alpha of f1. And similarly, I can do it for 100 trees or like m number of trees here. So my total model will look like f of f is equal to f0 plus alpha f1 plus alpha f2 and so on till alpha of fn. Yes. Can the alphas be different? Yes, but then you have to uh, pick so many hyperparameters. Here alpha just makes one hyperparameter, so your choice. But in typical case, alpha is generally chosen as the same rather than alpha 1 f1, alpha 2 f2, and alpha m alpha. Yes. Fine. And so like why it should work, and like what is happening. So like current model makes predictions, you calculate where the model is going wrong, that is residuals, you train a new model to fix this error, and then you add a correction to basically the second model will correct whatever the error the previous one gives with some learning rate alpha. Yes. Alpha does what? It controls how much each tree contributes, basically how much we try to rectify the error from the previous one. Small alpha basically says we will try to correct but slower. Large alpha will give aggressive updates. That means we try to close it very closely. If we do a lot of trees or a lot of aggressive alpha, that means alpha is higher, then it will end up with overfitting. That means we are exactly trying to match the training set, which we don't want to do because this is again overfitting. Yeah. And analogy here comes from basically student learning. So every time we give you exams, basically you learn from one exam, then you come prepared. Okay, this is what I missed. I need to improve on this particular thing. I'd go for the next exam, so on. Yes. Most of you have done this exercise already. So this is the analogy. And now gradient, or like why it is called gradient boosting per se. If you can think of a technique, of course, it looks like every time we find a residual and we try to move in the direction to reduce the residual, right? So gradient descent, what it moves the parameters to minimize the cost function. It uses gradient to find the direction and uses learning rate for the step size. Yes. In gradient boosting, we do the similar kind of stuff. We add models to minimize the prediction error, and we use the residuals basically as gradient proxy, right? So we predict something, but what we are missing, generally we find by gradient the directions and all, but here we have only the residuals that tells us, okay, this is the difference. And then we put as an alpha to find out what it should be the contribution. It's like a learning rate for that. Yes. So residuals basically show, okay, if residual is positive, then I need to add. If residual is negative, I need to subtract, let's say, in that direction. So that is what shows me directions. And yes, that is what gradient comes from. And learning rate is simply borrowed because in gradient descent, we call it learning rate, here also learning rate. Now, what are the hyperparameters in gradient boosting? Number of trees, of course, like how many number of trees, like M, let's say. More trees can also improve accuracy because each tree tries to correct the errors of the previous. But if we keep on correcting the errors, we will end up with a single model which is absolutely correct. We don't want that. That is overfitting. Yes, that will do end up with high variance. Yes. So what about alpha? We discussed generally smaller trees are better. Yes. Well, the smaller alpha is better. The problem is if you do smaller alpha, you will require a little bit more trees. More trees end up in taking more time to train. Yes, because it is sequentially done. Typical range will be like 0.01 to 0.3. There is no hard and fast guideline. If you look at a research paper while you are trying to implement, let's say, random forest or gradient boosting, typically you can check what the previous papers used and follow the same like ranges for alpha and all. And tree depth is around like 3 to 8, that is best, but it depends on the data set. It's not that hard and fast with the 3 to 8. And of course, deeper trees you have, they'll slow to train, slow to predict. uh, you use shallow trees. That's the idea of weak learners. Here training is slow but prediction is fast because you can still do a parallel prediction. Yeah. Now, gradient boosting for classification, it's similarly done, but like the idea is a little bit different. So here, what you do is you calculate the probability, and the function is given to you, which is again a linear function, though it doesn't change much. Now, algorithmic differences you again kind of like compute the same gradients and you train the tree on the gradients instead of residuals and use line search to find. So here instead of because there is no absolute value of difference because this is a classification setup. So here we try to find, let's say, the actual gradient. Yes, in classification it changes to actual gradient because there is no residual as such. There is no difference that you can calculate because the output is either 1 or 0. Right? So that's why here we use the gradients to find out what is this one. There is no residual in classification task using gradient boosting. Now, I'll just try to summarize. So, like random forest versus gradient boosting. Random forest is very parallel training, super fast. It reduces variance, harder to overfit, good default choice, less sensitive to hyperparameters. Gradient boosting, sequential training, slower, reduces bias. Yes, and can overfit with too many trees. Often, generally higher accuracy, but too many trees will spoil it, and more hyperparameter tuning is required. It's sensitive to hyperparameter. The rule of thumb, as I told, random forest first, gradient boosting for maximum accuracy. And this is just because those who are doing projects here or their PhD also, like wherever you are, majority of you will end up trying random forest and gradient boosting because these are really good algorithms. Yes. Uh, and the next one is like modern implementations, of course, like we have scikit-learn has random forest and classifier and regressor both. Gradient boosting, there are many methods like ADA boost, XG boost, light GBM, and cat boost is there. All of them are popular in their own way. Which one is better for my concern? Generally, like there are charts available on the scikit-learn. You can check which one to use particularly. Once it works, then you can find out a little bit more. Yes. When to use ensemble? Of course, like generally when we require a little bit higher accuracy, and if we have no concern for interpretability, ensemble is great because I told you across many trees finding the path is difficult. Limitations, of course, like it is complex and single models, hard to interpret, and definitely longer training times, right? Training one tree versus training 1,000 trees, even if you do parallelly, it requires more compute. It's not just randomly faster, right? It requires across many cores you can train. That their advantage exists for random forest, but still, as a compute time, it is still very long. Yeah. So this is one I just want to end like today with this, like bias and variance trade-off is real. Please understand the definition of bias and variance really well. This is one of the most fundamental challenge in machine learning. It's present today also. Yes. If you understand it well, the idea is you can apply the correction methodology correctly. Yes. Where we want to increase the training set, like this all understanding if it is a problem with the bias or problem with variance, if you understand that, then you can apply the correct mitigation measure. Yes. Where should regulation come? Where should ensemble come? Where should we increase the training data site? Where is the hyperparameter issue? All this will come from your base understanding of bias and variance. Yes. And again, there is no sweet spot. It basically depends on the problem and the data size. Yes. Ensemble learning, I told you, like combine weak learners into a strong meta model, and random forest reduces the variance, gradient boosting will reduce the bias, and it definitely often achieves the best predictive performance. Yes. And practical wisdom is, of course, beating ensemble methods is very hard using even deep learning. Uh, People have spent like years and years to find out deep learning that can beat ensemble methods. As of today, of course, deep learning beats ensemble in most of the tasks. But the idea is if you have a new problem statement, finding a deep learning approach to solve this will be very difficult. Uh, Using ensemble will give you somehow a good answer. To improve on that, you can use deep learning and other stuff, but that will take more experience how to fine tune them. This one I just wanted to put that low bias and low variance. Regularization will reduce the variance. It will prevent overfitting, but it will also increase the bias a bit. Yes, but overall it reduces the variance. So we reach towards low bias and low variance. Yes. Ensemble bagging will try to reduce the variance, and boosting will try to reduce the bias. Yes. And so wherever we have overfitting, use bagging. Wherever we have underfitting, use boosting, and so on, so forth. Yes. I hope that this particular slide gives you an entire picture. Like if increasing complexity decreases bias and increasing variance. This you can use as a cheat code while doing this exercise. Underfitting and overfitting, again, definitions I have written for what you do in underfitting. So if you have an underfitting, try gradient boosting, increase model complexity, add more features, reduce regulation. Yes, everything underfitting. If you look at if you guess, then if you find out if it is underfitting, you can try all these four methods. And if you find out if it is overfitting, try random forest, add regulation, reduce model complexity, collect more training data. So, and to understand what is underfitting and what is overfitting, bias and variance definition is important to understand and learn and remember and practice. Uh, so that is all I can say about bias variance trade-off and ensemble. So that basically we have covered simpler algorithms, but today we have touched on relatively complex. And these are the algorithms, random forest and gradient boosting. Which one will most likely give you answers for your project as well as general starting work? Yes, and it will be very hard to beat them also. Yes, in general practice. Fine. So with this, I end. I have a notebook ready, but there are a few changes to be done. So what I'll do is I'll share it on the course website. So please give it a try on your own. Yes. Uh, and yes. So if there are any other questions, please let me know. Yeah.
Shivankar, I wanted to make a couple of
Yes.
comments, and I
Yeah.
do have a question.
Yes. Yes.
So the first comment is that for everyone, I have just shared on the chat a name of a book for beginners. This is absolutely fantastic. So if you want to get a good idea of what is bias, what is variance, what is bias variance trade-off, or even what is bagging, boosting, and the random forest model pictorially, very with little mathematics, not too much mathematics, very nicely explained in this book. So you can have a look at this. Your concepts will be absolutely clear if you go through this. Then, of course, there are more advanced texts,
Yes.
but as a starting point, this is really nice. The other thing is that in our experience also, if your training data is not large, random forest, that is perhaps ensemble methods in general, beat deep learning methods, neural networks. Uh, the question I have is that the ensemble methods in general, are these conceptually the same as what is called a committee machine? How do I view this?
Okay. Okay. Committee mission. Maybe I don't know about that thing.
Okay.
Yeah. Yeah.
Yeah,
Yes.
that's a
Sorry.
term I have come across in papers.
Okay.
Uh,
Okay.
Maybe next time I can.
I'll also look into it. Yes, I
Yeah.
have not come across that word in that
The
sense.
idea
Yes.
is similar, that you have
Yeah.
different models, and then there is a sort of voting by those models, and then you come up with the final answer.
I see. I see. That is a general term as such, but this particular thing, like other than voting, there are a few other things that they do.
Hmm.
So, like bagging does this copy of data with like bootstrapping, like sampling with replacement, and random forest adds like subset of featuring. Gradient boosting like basically tries to correct the previous error rather than just voting.
Hmm.
Voting is eventually done because you have lot many models to ask answer. Uh, but typically their major importance lies in the bagging and the boosting technique as such in the ensemble, where they try to reduce this bias and variance maybe.
Hmm. Yeah, of course, that's the target.
Yes, yes, yes.
All right. The other announcement is that we next week we have a break the entire week, so no classes next week. We will have the next class on the 6th of October, Monday, after the holiday break. And in that class, I will start discussing, accessing, downloading data from various databases. Three or four we will directly work with. How to create your data set for model training, the kind of things that you have heard about. So I'll show you hands on, and I would like you to go through it along with me. So if you sit with your laptop or your computer and work on it as we go along, that will really be helpful for you.
Yeah, I think we have covered most of the top. I think we have covered all the basic topics now. I think they should try the notebooks on their own, and then we they should sit with us. I think we can take those tutorial kind of classes from
Right.
now on.
And as we go along, and for example, as I go along, as I discuss model training, maybe a particular model, uh, uh, we will again go back to the concepts that we have already discussed. Or if I'm using a particular feature, I will go back to the slides that I showed earlier, discussing the concept of what that feature is, how it is constructed, and so on. But with the additional thing that it will not be formal discussion, it will be actually how to do it. Okay, then.
Yeah.
Um, we'll see you all on the 6th.
6th, yes. And please complete your review on open review. I did not hear anything back. So if otherwise, yes, you can drop an email to the Gmail account that we have so that we can help you there if
Yes.
possible. Yeah. Okay. Thank you all. Yeah. Bye.